bienvenidos. Hoy nuestra conferencista invitada es la doctora Audrey Grockowiak. Ella hizo su pregrado y su doctorado en la Universidad de Estados Unidos en Nacional y su maestría parte en King's College London.
All good?
Yes.
Thank you. All right, can you all hear me? Yes? I think both should be on. Yes, no? I think both are on, right? Good afternoon, everyone. I am Audrey Grockowiak. I currently work at the National High Magnetic Field Laboratory in Tallahassee, Florida. I'd like to thank you all for being here this afternoon. There are many people that I would like to thank before starting this talk. So first, I would like to thank Paola for giving me the opportunity to be here and discover a little bit more of Bogota and of the campus. I would like to thank many of the funding agencies that sponsored our work. So the NSF, National Science Foundation in the US, the state of Florida, the Department of Energy and NNSA, and for this work, or for this trip today, I would like to thank ICE that sponsored my travel here. Other people that I would like to thank are at the MagLab, the Department of Public Affairs, Professor Greg Bobinger, who is the director of the lab, and my mentor, Stan Tozer, for sharing some of the slides that I'm going to show you today. And so I joined Stan Tozer's group in 2013. He's been my mentor for high pressure, and I would like to thank both him and my colleague, William Coliglio. They have been exceptional colleagues and mentors to work with. So today, the subject of my talk is physics under extreme conditions, or as you'll see in the end, the art of blowing up a perfectly working experiment. Extreme conditions in Florida can mean different things. So it can mean extreme weather with hurricanes, with humidity, extreme environment also with alligators, bears, or panthers. But for this talk, I'll focus mostly on extreme physical conditions about high pressure, low temperature, and high magnetic fields. So in the abstract for my talk, I put this quote by Dave Hokwang Mao. So Dave Mao is a pioneer in high pressure physics. He worked for many years in the US, in Washington, DC, at the Geophysical Lab. Now he's back into China, where he founded an even bigger high pressure lab. And in one of his papers from a couple of years ago, he said that high pressure should not be viewed as an extreme conditions, but more as an unexplored dimension. Consequently, our ordinary pressure world should be regarded as a special condition in the pressure dimension. And I think the same can be said of temperature and high magnetic field. So basically, the way we live here today, like one atmosphere, like Earth magnetic field, there is nothing, it's just like one special condition, but there is so much more to explore. And I would like to remind you and discuss a little bit about phase diagram. What's a phase diagram? I guess you've all seen a phase diagram. So it's just a graph where you have two or more axes. So most often pressure versus temperature. And I believe this is the first phase diagram that we look at when we're in high school. So looking at the phase diagram of water. And this is the most famous, I guess, phase diagram where you have the liquid, ice, and vapor or gas condition for water. But you can have different variables for a phase diagram. So not only pressure and temperature, but if you grow crystals, you can have chemical composition, solubility. So here I put, for those of you who do crystal growth, for example, the gold aluminum phase diagram with various eutectics. So that's one example of phase diagram. But here in this talk, I will focus mostly on external tuning parameters. So it's not anything that depends directly on your sample, but parameters that you apply outside of your sample. So in our case, temperature, pressure, and magnetic field. And those are very important for thermodynamic work because those are thermodynamics variable and they're intensive in the sense that they do not depend on the mass of the sample. And just to remind you, pressure and temperature are scalar quantity, and compared with a magnetic field is a vector. So temperature would be the same wherever you are in the room. However, magnetic field has a direction, and it's going to be very important because you can rotate your sample in the magnetic field and look at different things. So just to remind you of the specific conditions of Earth, the average magnetic field, it doesn't change a lot, basically, around the Earth, so at the Earth surface. So between 25 and 65 microtesla, this is pretty small. The temperature, there is actually a wide range of temperature. So at the surface of the Earth, about 14 Celsius. And we can go to about minus 90 Celsius, pretty cold in Antarctic, or pretty hot also in the desert, so around 70 Celsius. But now, when you go inside the Earth, you can go to pretty extreme conditions of 6,000 Kelvin at the core. So we have a whole range of temperatures to explore on Earth, and they can do different things. And similar things, so for pressure, we live in a 1 bar world. But actually, when you go down to the Earth core, you go to about 4 megabars. So you have also this whole range of pressure you can explore. So those are some of the things that I want to talk about today. So what can we simulate in the lab for those various parameters? What are the techniques that we can use to replicate those conditions? Can we go beyond those parameters? And what else can we learn? So here is the outline for my talk today. So first, I will give a general introduction to high magnetic fields. First, I will give you a few examples of what is important or what is interesting right now to look at with magnetic fields. And then I will show you some of the current technologies to produce really high magnetic fields. Then I will talk about high pressure. So what can we do with high pressure? What can we look at? How do we achieve high pressure? And I'll share with you the hottest topic right now in high pressure physics. And finally, I'll share some of our research combining both high magnetic field and high pressure. So let's start with high magnetic fields. So there are different things that we can do with high magnetic fields, and those slides are actually taken from some of Greg Bobinger's talks. And those show actually some of the work that we can do at the MagLab. So we can look at energy-related materials. So remember, so when you take a charged particle and you put it inside a uniform magnetic field, this charged particle will go into an orbit motion. This is the cyclotron motion. And this cyclotron motion has a specific radius. And this radius is defined by the mass, the velocity of the particle, its charge, electrical charge, and the magnetic field. So basically, the higher the magnetic field you have, the better mass of a charge resolution you have to identify the particle. And so this is the principle of ion cyclotron resonance technique. So ion cyclotron resonance is used at the MagLab to look at petroleum and metabolic compounds. So petroleum, or oil, is actually a very extremely complex material. So it's composed of over 100,000 different molecules for oil. And what's fascinating with oil is that depending on where the oil is sourced around the globe, so depending on which oil well it comes from, it has a very distinct signature, so it's like a fingerprint. So at the MagLab, what that team of scientists do at the ion cyclotron resonance facility is that they sample different oils from all around the world, and they do a fingerprinting basically by looking at the ion resonance signal. And that's an example of signal that they get. And they went further by doing Fourier transform, ICR, and this is basically the type of result that they get here. So looking at the mass over charge ratio, and they can really clearly identify different molecules. And this is compared, the green curve is compared with computing techniques in different labs. Looking at life, or live things. So basically, The first thing that comes to mind when we talk about magnet in life would be MRI, so magnetic resonance imaging. So if you've ever been sick or if you've ever had an accident, maybe you had to go into an MRI and have either your knee or your ankle checked. So this is some of the things that we do at the lab. So going from in vitro to in vivo and looking at biomolecules, cells, or organs by basically doing MRI. And our sister facility in Gainesville in Florida has a 1.4 Tesla magnet with a pretty large bore. So the center of the magnet is about 40 centimeters big. And you have to compare that with standard MRI for where you can fit a human being. So those MRI magnets are between 1 and 3 Tesla. So you compare it with the 11.4 Tesla for that facility. And they can do different works, different types of research there, but here one example that I show is some research on the brain. So they can basically look at live animals, so looking at rats, for example, and look at the way their brain behaves when you do different things. So for example, here you have the picture of a rat in a magnet. The rat is alive. Actually, it's a female rat nursing pups here, so you have small rats. And in that study, they were looking at the response of the brain when the rat was nursing the pups. Going back to what I do for a living, so I am a condensed matter physicist, and this is going to be the focus of the rest of my talk. So we use high magnetic fields to tune electronic interactions and also electron and lattice interactions. So you can look at many different things. You've heard maybe about topological insulators, fractional quantum Hall effects, and graphene is a perfect example for that. You can measure the Fermi surface of your compounds, and I'll talk about quantum oscillations tomorrow, frustrated magnets or superconductors. And I'll just give you like 2 examples today. So for unconventional superconductors. So first, what's a superconductor? So a superconductor is a material that when you cool it down, it conducts electricity without any dissipation. And so this happens only for specific conditions. So when you cool down below one certain temperature, you can apply a given current, but when you go beyond a critical current, you destroy the superconductivity. And same thing with the magnetic field. When you apply it to high magnetic field, you also destroy the superconductivity. So you have a limited phase space of temperature, field, and current where the superconducting state exists. And the first theory that described superconductivity was the Bcs theory. And that theory described very well the first superconductors that were discovered. But then in the 70s, 80s, more exotic superconductors were grown and realized. And actually those do not follow the Bcs theory, and no one really knows why. And there's no clear theory right now as to why those superconductors behave like that. So there are several families. So one that triggered a lot of attention in 1986 and since actually 1986 is the family of the cuprates. So they're basically copper-oxygen planes where the physics happen, and you have different layers of different atoms that actually define what's happening in the copper-oxygen planes. And that family triggered a lot of interest because they were discovered as the highest temperature superconductors at the time. So at that time, that was 92 Kelvin, which was really high. And then other superconductors, heavy fermions, so uranium-based or cerium-based superconductors, or also molecular superconductors. So it was found after like a decade of work that actually all of those unconventional superconductors share a universal phase diagram here. So again, the phase diagram, so temperature versus here chemical doping, but pressure also can be used as a tuning parameter. And there are similar ingredients in the phase diagram for all of those families. So an insulating phase, so you start as an insulator. Then as you increase the doping or the pressure, you get into a metallic and superconducting phase. There can be some weird things happening here, so either pseudo-gap phase or charge density waves, so more exotic electronic states, a strange metal, and so Paula is also an expert in strange metals here. And as you go to the other side of the phase diagram, things go back to normal and to a Fermi liquid behavior. What's really interesting here is that the superconducting dome, so the superconductivity here is maximal around a quantum critical point. And it's really difficult to really identify what is a quantum critical point, and it's not explained why the superconductivity is stabilized around that point. So there are many things to still to understand there. So those superconductors can be actually very tricky and full of surprises. So I said that traditional superconductors can be or are usually destroyed, or superconductivity is destroyed by the application of magnetic field. But it was discovered recently that actually for some superconductors, when you apply the field, superconductivity can be reinforced or appear at other places. And that was the case. That was a very recent publication on that compound, uranium ditelluride, that was discovered by two competitive groups, one in the US and one in France. And this is again a phase diagram with the magnetic field. And here this is the axis of the crystal along which the magnetic field is applied. So if the axis of the magnetic field is straight parallel to the sample, it was found that there is this general pocket of superconductivity that's then destroyed, but then there is this other pocket of superconductivity that appears and that's reinforced to pretty high, actually, magnetic field here up to 35 Tesla. So this is like really high. And then something even more extraordinary happened, like when they rotated this sample of magnetic field, they found this new pocket here in superconductivity that persisted to even higher magnetic fields. So this is very recent work. Nobody quite understands what's happening with that superconducting pocket. And that's for me like one of the next hot topics in physics. Maybe you've heard of frustrated magnetism. So that's my second example for today. So frustrated magnetism, so I think you've all seen this picture of a triangular lattice where you have spins in different directions. And since the spins only has basically two orientations, you'll have like two spins up and one spin down, or any combination, and you'll have frustrated magnet because you cannot satisfy a good condition for that. So there was one model developed by Shastri Sutherland in the 60s, 70s. So it's a theoretical model of an entire ferromagnet frustrated magnet. That's the lattice. And what's really interesting is that that was first a theoretical model to play with frustrated magnets. But recently, one compound, that compound here called SCBO, was found to be the first experimental realization of this theoretical model. So physicists got really excited because they could finally test this theoretical model in real life, in real experimental conditions. So this is the structure of this sample. So the blue atoms here are the copper atoms. They're organized in pairs. They're called dimers. And those dimers here are orthogonal one to each other. And so this is here the creation of the frustrated magnet here. And they form layers. So this is this layer here, separated by strontium atoms. So this discovery triggered a lot of experimental work. And it's fascinating because they did not predict, Shastri and Sutherland did not really predict what happened then. So when we apply high magnetic field, you basically go from an antiferromagnet to a ferromagnet because you align all of the spins along the field direction. So when you have applied all of the spins, you get to a ferromagnetic state where you have reached the full magnetization saturation, but it does not appear gradually or on-off, but actually appears as magnetization plateaus, so fractional amount of the full magnetization saturation. And you can see it here on this plot. So the magnetization as a function of magnetic field, and you're looking at this curve here where you see steps appear in the magnetization. So it only looks like steps. It doesn't look like much, but first, there is no theory behind that. That was not predicted, so nobody really understands the mechanism. There are several propositions, but nobody really understands why those steps appear and why it's really like integer fractions of the full magnetization. And again, look at the scale for a magnetic field. Here we go like beyond 100 Tesla. So 100 Tesla is just like a fantastic accomplishment to see that. And we still have not reached full saturation. So again, we did more experiments on that, and this is like the perfect example as to why theory and experiments have to work hand in hand to look at quantum magnetism, for example. And those were just a few examples of what we can do with magnets, but if you want to learn more, you can check our website, nationalmaglab.org. So now, how do we make magnetic fields? So if you remember from your electrodynamics classes, when you have an electrical current, you have a magnetic field that develops perpendicular to that current. So now when you take your electrical wire and you make a loop, basically you concentrate the magnetic field here in the middle. So you can play with that. You can make small coils, but you have to go from those small coils to bigger coils. And you have to be able to put a huge amount of current inside those coils to get to higher magnetic fields. The problem is that the more current you put in the material, the more you're going to warm the material. So if you want to have a working magnet or a magnet that lasts for a very long time, you need to find a way to cool down your magnet. And this is what Francis Bitter developed. So this is called the bitter plate. So it's basically copper or an alloy of copper. And here you see different slits and holes. And those holes are actually used to push some water through the coil to cool it down when the magnet is working. So at the MagLab in Tallahassee, we have the world record right now for resistive magnets. So we have fields that go from 35 to 41.5 Tesla. The power is of the order of 30 megawatts, and we have to cool down. So we use basically 2,000 gallons per minute at a certain pressure, so 17 bar. So this is a huge facility. You just don't have that in your lab here. You really have to have this massive installation that goes with it, the power, the cooling water, and everything. And so if you see, this is almost to size. Here, the center of the magnet, we call that the bore of the magnet. It's of the order of 32 millimeters. So this is 32 millimeters is rather small. It means that you have to fit all of your experiments in 32 millimeters. So it means your cryostat, your probe, and in my case, also pressure cell. So you have to be able to make really small things. So those are resistive magnets. I spoke about superconductors. So after the discovery of superconductors, people made industrial superconducting magnets. And one example I've mentioned is MRI magnets that you can take for medical purposes. But for the lab, you can also get superconducting magnets. So 16 Tesla magnets are commercially available. At the MagLab, we have 16 to 20 Tesla. And we are also working on the next generation of magnets, so up to 32 Tesla superconducting magnet, which is a world record. So it should be available soon for users of the MagLab. And the next magnet, which was a true achievement about, I think, 15 years ago at the MagLab, was combining both technologies of resistive and superconducting. So it's basically a superconducting coil, or several superconducting coils, and a resistive magnet at the center. So by basically combining the best of the best technologies for the resistive magnet and superconducting magnet, the lab in Tallahassee got to the maximum field of 45 Tesla. And right now, it's the only lab in the world with that capability. So in the Netherlands, they're also working on developing a similar magnet, same thing in France. But right now, the only static field lab in the world that has 45 Tesla is Tallahassee. Well, I'm lying. There is one lab also in China that opened one not that long ago, but so Tallahassee has the flagship for that. And it's actually a massive beast. It weighs 35 tons, and you have to cool down both the superconducting magnet, but also the resistive part. So it uses 4,000 gallons of water per minute at 31 bars. So this is massive, and it basically looks like that, seen from below. And for height comparison, I think I would be like this tall. So this is a massive beast, and it's a privilege to be working on that magnet. Then, if you want to go higher than 45 Tesla, you can go to pulsed magnetic fields. So you're no longer in the static regime. You can no longer stay for as long as you have energy to like 45 Tesla or so. Pulsed magnetic field means that you have smaller magnets, mostly made of copper or copper alloys, and you send a huge amount of energy, a huge amount of current in a small fraction of time. And that enables you to go to fields, for the moment, as high as 100 Tesla. And so those magnets can be either powered by a capacitor bank, so it's like capacitors, but like much bigger, so a whole capacitor bank. You charge it for a while, and then you just pulse this amount of energy in the magnet, and this is the field profile that you get for various systems. So here, magnetic field as a function of time, and the duration of a pulse is of the order of 100 milliseconds or so. It depends on the magnet. So, so think about that. So 100 milliseconds. So you have to be able to do all of your experiments in 100 milliseconds. So you need to have like super fast electronics, and you need to adapt your whole environment actually to 100 milliseconds. So, so it means also that you have a really steep field gradient. So you go basically from 0 to 100 Tesla in 50 milliseconds. So you have a field, large gradient of magnetic field, and if you have anything that's metallic, it's going to develop Foucault currents, and it's going to heat up your experiment. So if you want to do low temperature physics, you have to adapt your setup, and you cannot use like standard fridges that are made of metals, so you have to use like plastic fridges and plastic everything, basically. So where can you go to do those experiments? So in the US, we have several facilities. So in Florida, in Gainesville, and in New Mexico, so at Los Alamos National Lab for the pulse magnets. And let me see if I can make this work. So this is the first video of the first 100 Tesla pulse at Los Alamos.
It's been the holy grail of magnetism for decades. A magnetic field 2 million times stronger than the Earth's. A goal known as 100 Tesla.
It's something that we've been promising, we've been trying to achieve and planning on how to achieve for such a long time now.
For more than a week in March 2012, scientists at the Los Alamos National Laboratory campus of the National High Magnetic Field Laboratory worked feverishly to ramp up their biggest magnet for the world record 100 Tesla try. But it's not just about the record. It's about doing cutting-edge science along the way.
On today's run, there have been 8 different samples from 6 different groups around the world. And it's been a case of several weeks of long nights making sure these experiments work in a lower field magnets.
A 100 Tesla non-destructive magnet has a major effect on a wide range of science. It's a one-of-a-kind tool for studying the fundamental properties of materials, from metals and superconductors to semiconductors and insulators.
We have about a 2.4 megajoule capacitor bank that we energize the smaller magnet inside of a much larger magnet. So we're able to distribute those huge forces across a very massive magnet system.
Roger, we're all good to go. Start time now.
tense moments, the scientific team waits in anticipation while diagnostics measure the magnetic field strength and correct for any anomalies.
We have engineers that we work with that said you've got lots of design margin, but you know you're in unknown territory. And so if somebody hasn't done it before, then you really don't know, can you do this? It took years of commitment, it took years of vision, years of perseverance, to make this happen. Teamwork with a capital T, cooperation from the National Science Foundation, the Department of Energy, NMSA, Los Altos National Laboratory, Florida State University, and the state of Florida all worked together and contributed quite a bit to make this happen. So it was an incredible teamwork, a bunch of different agencies, and a group of really dedicated people.
The final official number, 100.75 Tesla. I'm Kevin Horwick for Lab TV.
So if you think about it, that's quite an achievement. So 100 over 100 Tesla. The bore of that magnet is 10 millimeters, so you have to fit one probe, the cryogenics, and they said that they had 8 experiments working at the same time for that one pulse. So that's a considerable achievement. And I remember Greg Bobinger, so the director of the MagLab, commenting on that video, physicists can't dance, really. So we have to work on that. So if you want to come and work at the MagLab, we are a user facility. We host users from all around the world, and the next call for proposals is November 1st for January to May period. So if you're interested, come and join us. And also take into account of the other facilities in the world. There are 4 MagLabs in Europe. So this is the European Magnetic Lab, EMFL, European High Magnetic Field Lab, 2 in France, static and pulse field, 1 in the Netherlands, and 1 in Dresden, Germany, 2 in China, static and DC, static and pulsed, and a bunch in Japan. So all of them are like fantastic places to go and do experiments. So now let's take a look at high pressure. So high pressure, you can find high pressure in absolutely all of the aspects of science. So here I have the example of high pressure biology. So you have living things here on Earth, like at the Earth's surface, but if you think about like the rest of the Earth, so the oceans, for example, so you know there is the Mariana Trench. This is the deepest trench in the ocean, so it goes down to 11 kilometers. The pressure down that trench is about 1,000 atmosphere, and scientists keep discovering living things at those extreme pressures. So there is this snail fish that was discovered in 2017. So it was brought back from those depths, and like the scientists said, well, it doesn't look like much, but seen at the depth, they're really quite magnificent. And I find this absolutely fascinating because those are like fish. They basically have the same biology as we do, but they live at like 1,000 atmospheres, so it has to tell us something about the way those organs work. So there is this whole branch of biology under extreme conditions that's really fascinating, and you have also to question yourself about astrobiology. So if you look for life somewhere else than Earth, what would it look like, and what can we learn basically from what we see on those extreme conditions on Earth to look for life somewhere else? High pressure biology. And if you take a look, for example, at cancer research, so what's cancer? So in the simplest way, cancer is just a bunch of cells that grow abnormally. So locally, in one of your organs that has a cancer, you have a huge amount of cells that have grown, and this creates a local pressure. And there is a whole branch in medicine that looks at pressure and the effect of pressure on cancer cells. And there was that paper that showed that an elevation in tumor pressure affects the efficacy on cancer treatment. So even though you find a cure for cancer, you have to be sure that some pressure effects actually do not affect that cancer treatment. I was at a conference recently in Czech Republic, in Prague, and so they're big on beers there. And I found that high pressure can be used also in the food industry. So there are actually people that they compare the tastes of beer depending if they've been pasteurized for conservation, or looking at hydrostatic high pressure. So they sampled various batches of beers, either pasteurized or high pressure, and they found that actually high pressure treatment of beer, they had lower bitterness than the one pasteurized. So that's also a way to do high pressure. Going back to more physical topics, for geophysicists, so you understand that if you go down to the core of the Earth, where you have like 400 megabars, you have to understand how the various minerals were formed under pressure. And for geophysicists collecting samples, you have to understand where those samples were formed and what you can learn from that. And also, can we reproduce them in the lab? Here, I'll put back this phase diagram of water. And that was actually the simplest form of the phase diagram of water. But this is actually one better phase diagram for water. It's much more complicated. So the gas phase and the liquid phase are still very similar. But actually, the ice phase has many different phases that are very different from a crystallographical point of view. So again, if you look at water somewhere else, if you want to know if you have water in other planets, you have to understand on which form water would be. Like if you have planets with different pressure or temperature conditions, what do you expect to find for water? And also on Earth. So there was this research that was published last year, 2018. So it's an effort that was led by someone at the University of Nevada, Las Vegas, Oliver Choner. And what he did was actually fascinating. So he took various diamonds for all around the globe from different mines, either in Africa or in Australia. And he looked at water inclusion in diamond. So basically, diamond forms at in the depth of the Earth, and when they form, they can trap water inside them. And then, by looking at those inclusions of ice inside diamond, he found that there is actually more water on Earth than we expect, and in different forms. So he identified a new form, ice 7, and that makes you question how much water you have on Earth. And it's basically, he said, it's another piece of the puzzle in understanding how our planet works. So there is still a lot we don't know about our Earth. So going back to condensed matter physics, which is what I do, pressure is again a thermodynamic variable. So we can change various things when we compress a sample. So we change the interatomic spacing. We bring the ions closer together. We can change the various angles also. This can trigger structural phase transition. So we can go, for example, for body-centered cubic to a different crystallographic phase. It has effect also on frustrated magnets. So the frustrated magnet that I showed you earlier, SCBO, does very different things actually under pressure. And a growing work of interest right now is the synthesis of materials far from equilibrium. So you can actually pressurize a sample, you can laser heat it, and you can create something that's completely different, far from equilibrium. So also by bringing closer together the various ions in your system, you can also change the carrier doping. So you basically change the density of carrier inside your sample. And you can go from insulator to metal to superconductor transition. And this is like one of the current hottest topics right now in high pressure, and I'll talk more about that later. So the various units for high pressure. So 1 bar is basically more or less 1 atmosphere. We speak in kilobar for higher pressure, and 10 kilobar is 1 GPa when we go to higher pressure. So the Marianas Trench is 0.1 GPa, and the center of the Earth is about like 400 GPa. So there are different ways to do high pressure. And first you have to decide whether you want to do static versus shock compression. So either you want to put your sample under high pressure and keep it under high pressure, or create a shock wave that will basically destroy your sample, but you can go to much higher pressure. So you can go maximum of 400 gigapascal to the terapascal range for shock compression. And this is a completely different business. So I'll speak here only about static high pressure. And then there are different types of high pressure that you can create. You can do either uniaxial compression, so you take a sample and you compress only along one direction. And there are different ways of doing this, either by just compressing in between two screws, or gluing that to piezo resistors, or just taking two diamond anvils and just crushing your samples. And you can actually learn a lot from uniaxial compression. Or you can do hydrostatic compression. And hydrostatic means that if you apply a pressure in this direction, the pressure will be distributed evenly all around your sample. And you can do this by using different technologies, piston cylinder cell or diamond anvil cell. But they all need a pressure transmitting medium. So usually a liquid that will transfer the pressure all around your sample in a hydrostatic way. And today I'll speak mostly about hydrostatic pressure and how we do that. And I'll give you a brief history of high pressure physics. And it started in the 20th century with Percy Bridgman. So he was really the godfather of high pressure physics for us. He invented the clamped cell. So basically it's two anvils, here tungsten carbide, that were crushing a sample and that were conducted with clamps. And he got actually the Nobel Prize in Physics in 1946 for all of his huge body of work that he did on high pressure physics. He really started the field. And now in high pressure physics we have the Bridgman Award, so named after him. And it really recognizes like the top high pressure physicists. So it's what you get at the end of your career when you've done really well in high pressure physics. And so some people that got this Bridgman Award, so Dave Mao, whom I quoted at the beginning, and also Neil Ashcroft. If you've taken any solid state physics, Neil Ashcroft from Ashcroft and Mermin, so Ashcroft is actually a high pressure physicist and he got that award. So that was, Percy Bridgman was, he did some work in the 1930s, 1940s. And so the next generation of physicists, high pressure physicists, actually developed the DAC, so the diamond anvil cells. So there were, it was really a race between several groups. So at the National Bureau of Standards with von Valkenburg and the Geophysical Lab in Chicago. So this is the picture of one of their first diamond anvils that they used. And at the time it was like massive, so around, I guess that's 1 centimeter. And so they did manage to create the first diamond anvil cell to get to 25 kilobar. And that did not come out well, but those are basically pictures of their initial setups for the diamond anvil cell. So, and this is like actually quite big, so this is of about that dimension. And remember again, so now when we want to put that type of pressure cell inside the magnet, remember it has to fit inside like 32 millimeters, so there had to be massive improvements for that to be able to do high field, high pressure work. And again, so von Valkenburg and Jamieson gave their names to some awards that recognize either graduate students in high pressure or early career scientists in high pressure. Then several things happened that really pushed the field forward. So Pierre Marini in the 1960s, he introduced gaskets. So up to now what people did was just to take diamond anvils or other anvils and really literally crushed samples. So that was not hydrostatic. But that guy, Pierre Marini, developed the gasket. So a gasket is just literally a gasket, a joint, where you put that around your anvil, you put a pressure transmitting medium, and you go basically from crushing your sample to developing a hydrostatic condition around your sample. And that was a revolution for the field of high pressure. And so the next thing, also Pierre Marini and co-workers developed a way actually to measure the pressure inside the pressure cell by using the Ruby Fluorescence. So this is an example of a Ruby Fluorescence. So when you shine a laser light to a ruby, it sends back fluorescence lines, and those lines are perfectly calibrated in pressure, so they shift in wavelength with pressure. So that was an absolute revolution for measuring the pressure. So now for some really hot topics in pressure, what's really hot right now. So I spoke about insulator to metal to superconducting transition. So without any contest, the two major topics right now are the race for a metallic hydrogen and room temperature superconductivity. So those are the two holy grails in physics for decades right now. And so it started in 1935. So Huntington and co-workers, they predicted hydrogen to become metallic. So they had no idea what pressure would be. So they said, well, it's 25 GPa or higher. And in 1935, we couldn't go that high. We could go like in kilobars or so. And it turned out to be like very far from reality. And actually not much work was done then. Neil Ashcroft, again, so in 1968, pushed that field again. And he made that prediction that by applying the Bcs theory, so the theory for superconductivity, to metallic hydrogen, he predicted that metallic hydrogen would become a high temperature superconductor, like really high temperature superconductors. But again, like the diamond hand vessels had just been invented. That was really the beginning of real high pressure work. So Neil Ashcroft continued to push that effort, and that enabled a huge technological improvements and developments to reach the highest pressures. So now the current limit for diamond anvil cells is 550 GPa, and this is like massive pressure. And actually, so metallic hydrogen was found in 1996, but for fluid, and that was found under shock compression, so the other body of work for high pressure physics. But under those conditions, so 140 GPa and really high temperatures, around 3000 Kelvin. So that gave scientists an idea of what type of pressure to shoot for. But still, like, nothing was discovered. And again, Neil Ashcroft, he kept pushing and pushing the field. And in 2004, he predicted that not only hydrogen, but also hydrogen alloys, so hydrogen-dominant metallic alloys, could become very high temperature superconductors, but at pressures lower than metallic hydrogen. So that triggered a whole body of work, and it took actually 10 years of relentless work for high pressure to get to the first result. That was in 2015. And one of the biggest players in the field right now, Aramet, the Max Planck in Mainz, and at this time is a graduate student, I believe, Drozdov. They found the highest superconductor under pressure, so that was hydrogen 3 sulfide at 203 Kelvin. So that was a massive revolution in the field of high pressure physics and also superconductivity. And the other big players in the game right now are the group of Russ Hemley, so there he's now at Chicago, and his co-workers at the Argonne Photon Source. And in competition with, again, Aramet, they found that in lanthanum hydride, they reached superconducting temperatures up to 280 Kelvin. So we're getting extremely close to room temperature superconductivity. So this is pretty big right now in physics. The other big players in the field right now, so at Harvard, Axel Vera and his, I guess, postdoc at the time, Diaz, they were looking at the metallization of hydrogen, so not looking at the alloys, but still hydrogen, and looking basically at the change of color in samples. So when a sample goes from insulator to metallic, you're supposed to see a change in color and a change in conductivity. But that was a massive controversy in the field because hydrogen is extremely reactive, so you don't know what it's going to react with your gasket or anything. So they did see a massive change in color, but it was not clear whether it was like pure hydrogen or reacted with something else. And more recently this summer, Paul Loubert, so in France at CEA, observed, so with looking at infrared at really high pressures, 425 GPa, a first order phase transition to metallic hydrogen. And that was a really beautiful piece of work. And what was really interesting in that piece of work is that it could see a change actually in color and also in the electronic band gap upon increasing the pressure, decreasing the pressure, and re-increasing the pressure. So that was a really beautiful piece of work. So what's next? So we still need to get to room temperature superconductivity. We're not quite there yet. We need to really understand what those systems are. So we say it's lanthanum hydride 10, but we don't know exactly what the composition is. and we need to understand really fundamentally what those systems are. There is a scientist in China, Yanming Ma. So he does calculations. So he developed a software to predict structures, and he predicted that now not only binary but also ternary alloys made of 3 different molecules could become the next big hot topic in high pressure research. And then most importantly for the community, so how do we go from something that's metallic under really high pressure or room temperature superconductor to ambient pressure? And how can we get like some applications for that? So if you're interested in high pressure research, there are many conferences. And my favorite one would be the Golden Research Conference. It's a small crowd, about 200 people, and you really get to meet all of those big players in the field. So the next one is next summer. So if you're interested, just join us. And now, briefly for our simultaneous experiments. So how do we combine pressure and field? So some cells are commercially available, but if you're really a big player in the high pressure community, you're going to design your own pressure cells. And this is what my mentor at the MagLab, Stan Tozer, has done for his whole career. So he has built his own pressure cells. He has adapted them for the biggest magnets in the world, and he's really the expert, world leader in that field. So he's developed either piston cylinder cells or a diamond anvil cell. And we have made them work up to 25 GPa, down to helium-3 temperatures, and recently up to 85 Tesla in pulse magnets. So that was a huge amount of work for him. And just to talk briefly about those cells. So you've seen how bulky those cells are, so you had to find a way to shrink them. And what's really crucial for a diamond anvil cell is that you need to have those 2 faces of the diamond really parallel, perfectly aligned to reach the highest pressures. And he's basically found the turnbuckle principle. So usually you see them in tension, you put wires in tension. But he applied that to put those 2 anvils in compression. And this is here the schematic of one of our pressure cells. So you put the diamond anvils in those 2 end caps. There is a thread here. So one is left-handed, one is right-handed. You put those 2 cups in a body, that's this greenish part around that has matching threading. And if you rotate the body around, it brings the 2 anvils closer together, and that's how you generate and retain high pressure. So it's a very simple mechanism. It has only 3 parts, so you can make them really compact, and this is how you can put them inside a magnet. And this is a picture of our pressure cells, and they're actually rather small, and some of them are made of plastic so that we can avoid heating and vibrations in pulse field environments. So what kind of science can we do? So if we look at this compound, cerium, rhodium, indium 5, it's a superconductor. If we look at this phase diagram, pressure versus temperature. So if we look at pressure versus temperature, it's an antiferromagnet with a superconducting pocket at high pressure. And if we look at a 0 pressure, but as a function of magnetic field, there is a nematic pocket or charge density wave here that appears. But the big question is what happens here in this region of the phase diagram, so at low temperature, but pressure versus magnetic field. And basically, can we connect this superconducting pocket to this charge ordered phase here? So this is what we've tried to do. So that was a large collaboration, and we coupled basically samples that were designed by focused ion beam to have like really clear devices and really clear contact geometry. And we put those devices on top of a diamond anvil. So large collaboration with many different experts. So for high pressure, pulse field, low temperatures, electronics experts for pulse field, focused ion beam experts to prepare the samples, and also the best crystal growers to have the best samples in the world. We spent about 3 months over various runs in different facilities, either at Los Alamos National Lab or at the pulse field facility in Germany. We make all of our equipment, so we make our probes, they need to be made of plastic. We make our pressure cells. We make our own cryogenics for helium-3 and helium-4 made of plastics. We developed a bunch of the electronics. And altogether, one run is about 1 year of preparation. So it's a significant involvement for us. And so we can do in Dresden 1 pulse every 4.5 hours, because when you dump this huge amount of energy for 1 pulse, you need to let it cool down, and it takes 4.5 hours most times. So at best you get like 3 pulses per day. So you have to optimize your experiment. And here's a picture of actually 3 precious cells on 1 probe. So we can do 3 experiments at one time in during 1 pulse. So it's a significant team effort. So here we put the probe inside the cryogenics, then putting the probe and helium-3 fridge inside the helium-4 fridge. The magnet is cooled down with liquid nitrogen. It's somewhere below the floor here. And sometimes it works well, and sometimes it does not. And so this is a video of one of our pulses. So once again, the magnet is located somewhere below this wooden floor here. You have a pump station to pump on the helium and for the cryogenics purposes. Here you see our electronics rack. And here there is more electronics equipment for the magnet monitoring and temperature. And this is what it looks like. So the capacitor bank is charging. So, yeah, you can laugh. I cried. So again, this big puff of smoke that you saw at some point was the liquid nitrogen that was quickly evaporating. And the alarms that you hear after is, well, first the magnet blew up, so you have to, tell us that something went wrong. And also you have oxygen sensors, so it tells us that there is actually a lack of oxygen in the cell, so don't go into the cell. And yeah, no, it's not fun. So at that point, for that 1 pulse, we had a collaborator with us. That was a new collaborator. He was a postdoc in Switzerland, and he joined us for a different project. And that was the first pulse he saw in his life. And he looks at us and he's like, was that normal? No, that was not normal, no. So, so it took us about 1 week to recover. We had to rebuild our cryogenic systems. We lost helium-3, we lost many things, but we could be transferred to different magnets. And in the end, we did manage to finish that study and actually show that that superconducting pocket and that nematic state are actually not connected. So that's it for me. So again, so some takeaway messages. So if you want to do extreme conditions physics, you have to be ready to build your own equipment. That enables the science. You have to be bold and be safe. So sometimes things do blow up, but embrace the failure, learn from the failure. And this is what I have actually in my office that I look at every day. So fail, fail again, fail better, embrace it. Thank you for your attention.
You talked about the plastic cryogenics. Can you tell us a little bit more about that?
Yes, so we need plastic, so everything needs to be non-metallic, because when you have a big gradient of field, you're going to generate currents, and basically you cannot sustain helium-3 temperatures, very difficult. So, so my mentor actually, Stan, developed those plastic fridges. So it's a special, it's not plastic actually, it's a mixture of fiberglass and epoxy. It's called G10 in the US. So it comes in sheets that we roll up, so we call that actually a jelly roll, and we glue that together with more epoxy. And if everything is leak tight, it actually works beautifully.
But how do you assure a thermal equilibrium for that thing? Or you just do a constant temperature, you let everything thermally equilibrate, and then you perform this?
Exactly, so for pulsed magnets, you are at constant temperature. So we cool down at helium-3 temperatures, we let everything equilibrate, and we have different ways to measure that we are at base temperature. And then we do a pulse, and we don't actually heat up during a pulse. So, yeah.